So the title is might be a little bit wordy. It says, Heuristic Design of Experiments with Meta-Gradient Search of Model Training Parameters. But basically what it gets down to is, as a practicing data miner, there's a lot of choices. Choice is good, but it can be overwhelming a little bit. And so some of the questions that I'm going to discuss is, if you, some data miner, you've got a lot of algorithms. You know, maybe you're using R, you're using SAS, there's a lot of different packages you can use. How do you stay organized among all the choices? There's all the different algorithms, all the different parameters, adjustments for, you know, cost versus profit, or type 1 versus type 2 kind of error bias. So some of these things aren't just parameters on the algorithm itself. What's the target metric you want to select? How do you know, what's a process to go through to figure that out? Ensemble modeling has been very prevalent with the Netflix competitions, or the last KDD Cup competition. They were using ensemble methods as the winners. And so what's a good stage to add that to your project? And then also, as you're going through different data versions, pre-processing, trying new fields or new ways of representing metrics. And so the questions I'm saying is, how would you plan? How do you learn as you go? How simple should you stay? And sometimes there's a balance of descriptiveness versus complexity. Sometimes I've been in situations where I get pushed back and they say, well, don't get too detailed because we need to be able to tell a story. And so I have some thoughts on that. So my outline is, I'll talk a little bit about some example model training parameters, and I'll just use SAS Enterprise Miner as one example. But the same situation would arise in various other packages. And I'm talking about tracking some conservative results in what I call a model notebook. And it's kind of how to measure the progress. And then from there, I go on to how to plan and dynamically adapt, and then how to describe. So the main themes are measure, plan, describe, going over the life of your project. So in SAS Enterprise Miner, it has a data flow GUI. You can lay out these icons. And so in this first, these are different input boxes where I can select input fields. I could feed it to some program where I'll split out like the learning, tuning, validation sets for holdout. Maybe do stratified sampling if I want to. I can feed that to different modules. If I want to feed it to a regression module or decision tree, neural network, they have about 12 or 14 different predictive engines you can use. And so in the first module, so the ones that are circled are the ones I'll be talking a little bit about in examples. And one of the things I want to point out is it's not just one place you're modifying stuff. You're modifying parameters and choices all throughout the software. And you need to keep track of that. So in this data source, going in there, there's a decision matrix where you can have a weighting. So in this case, I'm looking at if I correctly find a fraud, in this case it was for checking, then I had one positive weight on how beneficial it is. If I forecast decision one, I think it's at risk of fraud, and they do the phone calling, it has some cost, but it's not as much as the benefit. And so tweaking these parameters in this kind of matrix is something that definitely makes a difference. And then with regression, in there they have different main effects. You can use two-factor interactions. So that's where the software will automatically multiply field A times field B, field A times field C, field A times field D, and they'll do a lot of the interaction detection for you. You can turn that off or on. Polynomial terms, that'll be as if you have field A times field A itself, so it'll be A squared or A cubed. So it'll do a lot of search for you. And some of this you'd have to do in pre-processing in other packages. So some of the pre-processing that would be in other packages come in as part of what you're searching here. And then just talking about neural nets. So I assume the audience is experienced with a lot of different algorithms, but so having a multi-layer perceptron is like having linear discriminants. Having circular regions would be like a radial basis function. And so that would be one of the parameters you can vary. How many different lines you have would be the number of hidden nodes, or how many circles you have if it's a radial basis function. So that's another one of the parameters. But you get too much, it gets to be too complex, and then it doesn't generalize. And so just looking at the hidden weights here, or you can have a direct connection from the input to the output. And so as you increase the number of hidden weights, you can detect more features, but then also you can get into more trouble. And you can do very well in the training set and not so well on the holdout set. Under the neural nets in this network drop-down box, they have about 24 parameters. Some of the things to focus that I was focusing on more is, choosing an MLP versus an RBF. Is it an open discriminant region or closed? Or have a direct connection from the input straight to the output. Solve the linear program, the linear part of the problem first. So getting into decision trees, there would be the tree depth, the size of the records in each leaf, and different ways of representing the tree. There would be like the tree depth, the minimum leaf size you could have, different ways of cross-validating in there, the different splitting criteria. That would be the difference between, say, a CART and a C5O or other algorithms. And then gradient boosting would be another tree family. That's where you might be doing a series of, say, 50 to 200 trees, where each tree is small. The first tree is something that's fairly simple, like 6 leaves, and it comes up with the initial forecast. Then the next tree forecasts the errors of the previous one, and so on for 200 or 400 times. And then it'll do testing on a holdout data set coming back. So I'm skimming through it quickly just to give an example. There's a lot of different parameters to worry about. And then if you have other software packages. So this one would be SAS Enterprise Miner, has a variety of things that you can search. This one would be R. That was just one assessment of how many models you can find. Some packages might be specific in one particular category, such as Bayesian networks or very focused on decision trees. So, if you have multiple software packages that you can use or libraries, then it gets to be even more choices to search through.
Which are the names there? Sorry, which packages are, I guess?
Okay, so this one was base SAS and SAS stat. So the general programming language. This one was Angus decision tree. This one is SAS Enterprise Miner. Let me see, I can't remember which one. Oh, this one was Oracle Data Miner, Salford Systems. And then this one was R. And then this one was Bayesian. So, but the main takeaway message is there's lots of choices. And how do you spend your time if you're running a project to go through all these choices? How broadly should you go? How much in depth should you go? And when should you move on to the next project? And so, are you feeling a little overwhelmed by lots of complex algorithm parameters? I don't know everything. I'm still learning by lots of stuff. And so part of it I have to figure out is, when am I going to investigate and understand something new enough to be able to use it? Or should I work on something tried and true that I know? So there's that balance. But a deep understanding definitely seems to help. And that gets to heuristics. If I have some knowledge on how things work or what the assumptions are. Sometimes I've worked with people with a master's in stats, and they would say, don't put correlating fields into your regression. The correlating fields will cause problems. But the reason it causes problems is because of the matrix inversion. If you train a neural net or you train a support vector machine, it won't have the same problem because it's being solved different ways. So understanding the math behind your algorithms, you can understand, well, some issues are an issue just because of the numerical method, and some issues are core to data mining, like will something generalize? So how can you manage the details? So that's what I'm getting to next, a model notebook. So that's a general data structure I was using to track my experiments. So model exploration process. I think of it as a scientific method of kind of hypothesis test. I try and change just one thing at a time. And a design of experiments is kind of like a test plan. This is what I want to go through in my project. But I don't have everything laid out from day one. I'll have some initial investigation, and then based on what I start with, then I'll decide how to continue on. And a key design objective is all experiments are reproducible. I was working on projects in the past where somebody said, oh, I created this great model, but I kept changing the code as I went, and now I have to go back. I'm on version 15, and version 7 was the best, but I can't reproduce version 7. I'm like, ah! So reproducibility is very good. It doesn't have to be anything as fancy as long as you can track what are the parameters, what are the settings, what was the data set. So that's something that would be very good. And also, a lot of times I'm using multiple software packages. And so I would use, before loading it into any package, I would do the splitting between training and test records ahead of time so it's consistent in all packages. Because I don't want the sampling to be something that's a cause of what a difference is. I just want it to be what I control, the one difference. So here, what I'm looking at is I have input parameters and outcomes. So I have data version 1, the different algorithms, the regression, neural net, 15 other things, and the model number in the series. So the first neural net, second neural net, third, fourth, et cetera. And then with the parameters, well, the parameters are change from algorithm to algorithm. So if it's for a regression, then how many variables do I give it? How do I do the variable selection? What kind of target? What kind of weighting would be some of the other parameters? For a neural net, how many variables do I give it? How many hidden nodes do I tell it? Do I have a direct connection from the input to the output? Is the architecture multiple layer perceptron or radial basis function? So I won't go into all the details, but all the things that you have to choose and change would be things that would be on the input parameter side. But it doesn't always have to be from the same menu. It can be anywhere in the process of what you can change. Now, I have a heuristic design objective. So for my project, it might be different than your project. But this is the design objectives I had when I was coming up. So I care about accuracy and deployment, reliability and consistent behavior. I want a general solution. So it sounds like a good assumption, but if you're doing targeted marketing for banner advertising, you're retraining your model every day, you may not care as much about consistent behavior because you're just going to train it again from midnight to 2 a.m. But I'm working on fraud detection and my models will be in production for a while. I don't want to have any penalty for model complexity. As long as it validates consistently, as long as the tool is useful, I'm happy with it. And some of the research papers I read, they do all this penalization. If it gets to be more complex, they try and pound down to a simpler model. My attitude or my design objective is as long as it stays consistent, I want to keep using it. And part of that message is, let me drive a car to work. Don't make me just ride a bike. I understand all the details of a bike, but not necessarily every issue of the design behind a car. So sometimes I have check writers, senior vice presidents that say, oh, you have to describe more, you have to describe more. And I try and push back on that a little bit with this analogy. Or sometimes the mathematical people will be very rigorous about Occam's razor. And I have a preference of pushing back against that. So my objective is I want to develop some kind of smooth, continuous metric to sort models. And I want to find out what will be best going ahead in the future. So in the different outcome columns, I have the training results, the validation results. So that would be fairly similar. And then I'm calculating this gap. And the gap is the difference between the training and the validation. The idea is a bigger gap is of more concern. I want to minimize senior vice president heart attacks. That's a big penalty for volatility in your models. The first person I replaced in my first data mining job was somebody that got laid off for that reason. So it got my attention. So I've got this gap, but then I wanted to use that as a penalty function. So I created what I called a conservative result. So for the conservative result, I'm using the worst case between the training and the validation. And then I added the gap penalty. And so if I get some models that are really accurate, but they have a bigger gap, maybe I'll accept that. And then I've got a model that's reasonably good, but not as good, but a very tight gap. And so this metric is trying to take into account both. So you can have one dimension that's accuracy and another that's generalization. And so I'm trying to pick something that's taking both into account. And there can be other ways that you might want to work on these. So my conservative result, for some metrics, higher is better, a bigger correlation, a bigger lift, a bigger profit. So my conservative result is the minimum between training and validation minus the gap. Some things that are error metrics, like mean average deviation or root mean square error, risk, lower values are better. So I just take the maximum between the training and the validation and add the gap penalty. Yeah?
You're not penalizing for complexity, but
I'm penalizing for lack of generalization.
have you tried any kind of DEF type measure or generalized degrees of freedom?
Sometimes. I mean, I'll use that when I'm designing how complex some of the systems may be. So, and I'll use that as I'm evaluating one algorithm against others. So I've looked at like the ratio of training records to free parameters across different algorithms, and I'll take that into account. But if I have concerns, sometimes I'll just have multiple holdout data sets, and I'll look at the gaps. How consistently is the gap? So.
Because you're trying to go more directly at what they were getting at, somewhat indirect.
Right. Yeah. So it's certainly valid that if you try and train a neural net with 1,000 parameters on 500 records, it's not going to work. You know, you want 10 to 1 or more, 20 to 1 training records compared to your free parameters. But then with some algorithms, it gets to be hard. How do you want to calculate the number of free parameters of a decision tree or a naive Bayes type of thing? So rather than trying to answer that question, I try and focus on, well, I'll try different metrics and I'll see what seems to hold up over time. And so since my focus is what holds up over time, then I've tried out different metrics over time. And I'll keep trying out metrics.
Can you explain like how the gap is essentially the absolute between the error training and validation error?
Yeah. So let's say here's the training. So let's say lift where higher is better. So for this first neural net, I got a lift of 6.6 on the training set, and on the validation, 10. The gap is the difference between those two, absolute value, because I don't want to care if what's larger. Okay, so this one would be bad. For this next model, it's a lift of 6.8, 6.7. The gap is very small. So here my conservative result is the minimum between these two, which is 6 minus 4. So that's a lift of 2. So that had a big penalty. I don't like that one. These two are fairly close, 6.8, 6.7. The worst is 6.7, and I subtract off 0.15. So that's 6.58. So then I can use this column as a sort order to pick which model I might want to put in production. So this is what I was looking at. So in the outcomes, sometimes I'll have different sets of these, like lift in the top 10%, lift in the top 5%, different places of where I might be deploying. In this case, if you're calling some percentage of the fraud basis, or if you're mailing or communicating with a certain limited population, then you want to look at the lift numbers.
And the other situation you were saying you will try to do the opposite, like root mean square or...
Yeah, because if it's then, so here it's always take the worst case between the training and the test, and I want to have a penalty for the gap. That's the attitude. And just how you change the signs is what'll be different. So, okay, so some of the heuristics. So I'll try a few models of many algorithm types to get started with. So get some basic things working. Maybe if I have 12 algorithms, maybe not everything, but at least the most common 8. Kind of seed the search. try a few basic things, the default parameters and a few reasonable things. And then opportunistically start spending time, more effort on what's working. You know, if you have some top stocks that are growing, put more money to invest in it. But you don't have to only invest in that. Still try a few trials on medium success. You know, it's like diversify your portfolio as some heuristics. And then after you iterate through that for a while, then start trying some of the ensemble methods, combining model forecasts with top source variables and some of the top models. And ensemble methods work if you have different kind of errors. So if you combine models of different kind of engines, then they're more likely to have different results and benefit from boosting or averaging. So continuing on, in this particular project, I did about 144 trials. And I had data version 1, decision trees were working well, 2, 3, 4. So I started simple, and then as I was working on things, I had other data versions where I was incrementally adding more complexity and adding more pre-processing, more complexity. And then where I'm going with this is this ends up being a data structure. So keeping track of all these trials can be input data for later analysis. So all of the parameters could be input fields, and the outcome, whether it's your conservative result or others, can be your target. Or you can forecast how long does training time take. So it's actually a search space. So now you're looking at searching which model training parameters lead to the best results. Okay, so I've measured progress with the model notebook. Now I'm talking about how do I want to plan and dynamically adapt. So there's different design of experiments. There's literature you can read on that and books and quite a bit. So one way is vary one parameter at a time, but that doesn't really work out with given so many choices that you have. And especially if you're working with large data sets, then the computation goes way up, even if the compute power is going up. So a simple way is just an exhaustive grid search where you try parameter A, low, medium, high, parameter B, low, medium, high, parameter C. Well, I didn't copy the matrix 3 times, just twice. So you can see this is going to be quite the exponent there. If I have 3 parameters that I'm searching with 3 settings each, you can get a little bit simpler with what's called a fractional factorial design. Say select 10% of the points, and so you can average over some rows and columns without having it be completely. But still, it's going to be growing very fast. Stochastic search, like genetic algorithms, you know, you have a directed random search. You know, if you have a huge space, that'll be a bit more efficient. But it can still be what I call overkill in complexity. If you have 100 models per generation, that means 100 data mining algorithms all competing against each other, and you are growing forward for 100 generations, sure, you can do a better job finding something optimal, but I don't want to train 10,000 models and get all the infrastructure. I'm a little more humble. I just want to get something going this week and next week. But it is an option. There's a Taguchi analysis. That's a type of design of experiments approach. And it's very good at doing search over these kind of design of experiments, planning the design of experiments. As one point, there's a company, Offermatica, that was looking at landing page testing for websites. And so you could have website layout A or B, where you have different colors, different layouts, different messages aimed at different segments. And so there would be 6, 10 different attributes you could test with that. And so by fine-tuning it, that was all a design of experiments. So that's one case of design of experiments being enough to fund a company, launch a company, and have the company have a successful exit. So, because Offermatica was acquired by Omniture in 2007. And it was basically design of experiments wrapped around by a vertical application. So there's some other places you can read more about it. Now, one thing is, it doesn't use much domain knowledge. So before I was talking about some of the heuristics, some of the experience that you as modelers may understand and know. So with the Taguchi analysis, then they have a particular structure that they are searching for through the parameters. So they have what they call an outer loop that's this context, and then the inner loop is the larger cube. So here they've got a plan to search through about 5 different parameters. And so it's got a particular process that they go through. There's books on Taguchi analysis. I'm not trying to cover all of it, just touch on it as an introduction. And it's not a full grid search. It's more efficient than that. But, well, I guess my question is, can we improve with experience in a heuristic process? So that's where I want to go. I like to keep things simple enough I can get stuff done. So for comparison, you know, when you have an algorithm like regression, the algorithm searches different weights. Neural net would search weights. A decision tree would search on different fields to split on and values to split on. So we have algorithms that are good at doing the dumb search stuff. Well, let's do a meta search. Not on the weights, but let's search on, for regression, do I do a forward variable selection or stepwise? For a neural net, what's the step size? What's the learning rate? For a decision tree, you know, what kind of metric to choose for optimization? So these are all sorts of things that we can search on. So on the model training parameters, or it could be on the weights, or how you design the target field. So I'm assuming that, you know, I want to train maybe 400 to 400 models. I don't want to train 4,000. I don't want to train 10,000. So I'm raising my hand and saying, this is my assumptions. You know, if yours are different, then you'll have different circumstances. I do want some degree of diversity to investigate different algorithms. So I'll use knowledge of interacting parameters. For example, I found that, you know, if you have cost and profit weights for your targets, and I do like a naive Bayes on that, the boosting weights after like the 10th boosting trial, 11th boosting trial, 12th, it'll wipe it out and it won't be paying attention anymore to the cost profit. So sometimes parameters fight each other. So I'll test those in parallel. So I won't do both boosting and a heavy weighting on the cost matrix at the same time. Delay searching very compute intensive parameters. So I'll try and first go over most of the things that are computationally reasonable. And then before I train a giant decision tree or giant neural net. So I'll try and get most of the other things reasonably stabilized so I don't have to train lots of compute intensive things. Get everything else done first. Okay, so here gradient descent is something that we're probably familiar with. You know, if you have some kind of error surface, you know, hilltops with high errors going down to beach and water for a minima, you've got some kind of river valley. Okay, so it's doing a gradient search. Well, this gradient search over 2 weights is very similar. You know, so we start off at a random spot and go through some process to find a minimum. We could end up in the different minimum. Well, I'm looking at trying to go through the same process, only trying to minimize a conservative result with respect to model parameter 1 and model parameter 2. So what I'm describing is a similar process, but it's actually fairly easy to do. So what I describe with is start with a reasonable default setting of the parameters, this center of the daisy, vary 1 parameter at a time from the center. That would be like each petal of the daisy. And then, so I'll try 5 different settings where there's only one thing changing. And then I'll change all 5. And that's like in the gradient descent, I start off at some random position, some reasonable default, and I'll vary, I'll try Gini versus chi-square, or I'll try some other metric, or some other parameter. And I'll check out through all of these and see what helps me be better than this default, and then I move in that direction. And I'll change multiple parameters. And then continue on and repeat the process as I'm going to the next one and the next one. And in a way, this is similar to, in the Taguchi analysis, they've got different context. You know, start off and you do a local search. So if you've got some kind of hill surface, some error surface, this is like saying, well, which way are things getting better? Which way is water going to roll down the hill, is what I'm trying to do. And so that has some similarities with doing searching through a path in the Taguchi analysis, but not exhaustively searching as much. So keep it simple, or simpler. And so just to make it more tangible, so here I've got the first model, that would be like the center, and the default parameters, and then I'll vary some things, the criteria from default to a chi-square. So that would be like a pedal. And then I have another default, where this particular row is the default settings. And I'll vary one thing at a time, I'll vary this, I'll vary these values, until it'll keep going through that, and then I'll come up with a new best. So what I'm doing is, I have a way of varying one thing at a time, and then I look at what the results are, and I go through a batch of what I'm searching. So I'll have something planned, go through, train a series of models, look at the results, and then I'll get my next starting position for a series. So I can have a directed search. And then with the final parameter settings, if I have a large amount of data, you know, millions of records, I might go back and retrain. So the advantage of this is I can use a medium amount of data to get started with, and then do a large amount of training on just the best settings. And then after I get some of that across the different model types, then try the ensemble methods, or like a gradient boosting. Right now, gradient boosting uses CART as a decision tree, but there's no reason you can't use a gradient boosting style on other algorithms. It's just train on like a 50% set of records, and then the next model forecasts the error of the previous one, and you sum them up. So that was some of the approach used by last year's KDD Cup winners, was with ensemble methods. They were doing averaging, having different forecasting fields by different models feeding into another model, and the next model was combining them together. Or with Netflix winners, they were using various ways of combining their model results. But you want to wait till you have other things kind of stabilized before you start combining the best ones. That's kind of like the teams merging. After the teams have kind of plateaued, they're not getting much better. Okay, so that was how to measure the progress with a model notebook, then how to plan and dynamically search, and then now how to describe a system. Because a lot of times before you go into production, you need to present to somebody. Who's a check writer? Who's the gatekeeper? So a lot of times I've had to present to check writers, the senior vice president, the owner, who wants a reality check. Does this make sense? Or what if analysis. If you want to fine tune a larger system. Sometimes if you want to look at some optimal allocation of prices or resources, then this can be your OR function that you're optimizing. And what you're doing is trying all sorts of different combinations of advertisements or advertising parameters. Sometimes you need a descriptive simulation, like if I talked to somebody earlier today who was at Lawrence Livermore, and so some of the data mining is for more doing a modeling of a physical simulation. What are the dynamics? So you don't care as much about the predictive accuracy, you care much more about the descriptive variables and how they relate to each other. I've talked to somebody else that was working on political donations, where they were trying to understand of the people who support candidate X, what are they motivated by? What do they care about? So sure, you want to reach out and say, call Tricia to get her to donate to your political party, but you also want to find out, well, what's in common with, say, Tricia and Paul and various other people? You know, if I'm going to represent this constituency that supports me, what are the dynamics behind them? Or other times I've done credit, where by law you're required to offer 4 reason codes. So if I'm going to turn Vera down for credit, then I have to give her 4 reasons why. And that would be different than why I might turn down somebody else. So these are some of the situations I've been in where I need some degree of description. But I don't want to cut my algorithm choices. So again, I want to get through some level of understanding, but I don't expect to get to every level of detail. When I go buy a car, I don't force a salesman to tell me, well, why did they choose this millimeter bore for the piston? I don't need to know some level of detail. So provide enough info to drive the car, but not enough to build the car. You know, a check writer, senior vice president doesn't have to understand a B tree to buy SQL. It's silly. So why should us data miners have to go through some level of scrutiny like that? So sensitivity analysis is one process that's fairly general out of electrical engineering. Yeah?
So when you said algorithms, I mean, given you have a problem, I mean, certain algorithms are kind of better known to solve that. Do you
Absolutely.
try all of them, or you just
No. I mean, I'll try and be opportunistic as it makes sense.
given the problem domain you're trying to?
Very much, yeah. And so I've worked in a few different problem domains, and so just as I start into a new project, I try and think of, you know, what can I leverage from my prior experiences? And so if I'm working on like internet advertising where it's 3 clicks and 10,000, or fraud detection where it's 3 clicks and 10,000, I may do one set of methods. But if it's on low data volumes, other methods, or large data volumes, different methods. So absolutely. So I'm very much in favor of the heuristics. So with the sensitivity analysis, I don't know, how many people here have any familiarity with sensitivity analysis or have heard of that? Okay. So I'll just go through this. So let's say you take 1,000 records, a random 1,000 records, and you run those through the inputs, and you get your output forecast. So that would be your default forecast. With this, you change each input record by multiplier, like maybe 5% larger. And then you see what the delta in the outcome is. So if a larger change in the outcome will mean that this input for a fixed increase is going to be more significant. And so then you average over those 1,000 records or so. And that'll give you sensitivity analysis. There's different ways of aggregating them. Average of just the absolute values of the deltas, or just the positive values, or just the negative values. You can get more complex with that. I've had luck doing clustering on those, or put them in Excel pivot tables and turn that over to a curious VP who wants to kind of understand, well, with this business segment, what drives the model, the prediction mostly? What's the high risk in this business-to-business segment versus the business-to-consumer segment? So sometimes turning over pivot tables on the sensitivity data can be very useful. And then for the reason codes, so I can come up with a sensitivity analysis to rank all the fields. And if I have some of the fields binned, like maximum late payment is 120 days, or 90 days, or 60 days. So I can rank these fields where a given record would be Mr. Smith might be 90 days late and bankrupt in the last 5 years. And so then that would become his first 2 reason codes. So then you can go farther down the list to however many reason codes are needed to describe it. So you can give both a global level description of a model and then a local at a record level. You know, what drives a forecast for Mr. Smith versus Mr. Jones, or the next record, or the next record. So the reason codes can be very useful. Okay, so to summarize, I was talking about one way on how to measure results, and I was advocating a conservative result. And then I was using the model notebook as far as how to plan and a particular process to go through with the design of experiments, and a particular way of searching through that to continuously improve my models. And then also I was describing how systems can be reasonably described. And fairly general, that's arbitrary of however many models you've combined or aggregated or boosted or any complexity, it would work. So So those are the main points I wanted to talk about. And the one takeaway is just the process of going from design objectives to heuristic design. So if your design objectives are different, you'll probably come up with different heuristics. But that would be something that's fairly generalizable as you work on other projects. You know, start off with what are the things I want, and then design with metrics that come up around that. So that was my talk. Other questions or comments? Yeah?
The heuristic meta-gradient search, I was wondering, how do you prevent, it seems like it would be susceptible to massive overtraining. Since you're basically running these things over, even though you have validation sets down below,
Right.
you're running them a zillion times, and you're eventually going to overtrain.
I don't run into that too much because I've got the training set, like a tuning set, a validation set. And so I haven't shown everything in the model notebook, or sometimes I would shrink it down. And so some of the times is once I get down to a final set of model architectures that work, then I can look at the gap between, say, the learning and the tuning instead of the learning and the validation. And so that way I can have another holdout, a second stage holdout. But I don't have to do it with all, say, 144 models. I'll just do it with, say, the last 10. And so the same healthy paranoia that I use to filter out early stage, but I don't want to have to do it for every model to do it twice. So I just do it opportunistically as I get near the end. But yeah, it's always good to have a healthy paranoia about memorizing the price of Tina in China drives your fraud. You don't want to pick up artifacts, absolutely. So yes?
There are like, commercial tools like SPS, I don't know about SAS, they actually provide this, what you just described. They will help you, based on your data sets, what models might work best. Do you know how those work? They use techniques like this where they identify the top models and then?
Well, I mean, when I was using SAS Enterprise Miner, they didn't have any particular guidance for using, this algorithm versus that algorithm. They had some ways that would create summary tables of model results. There was, in the 90s, I used a product called Neuralware that had about 18 different neural nets. And then they had a part of that was predict. And that was a genetic algorithm search over all the neural net parameters. But that would just run and run and run and run in 3 days. And I might see some improvements. But then if I came up with some creative ideas, I could beat it. And so that's where I was starting to appreciate, gee, heuristics are good. My experience isn't so bad. So it's kind of a trade-off versus the exhaustive search. So one of the links in here was on the Taguchi design was from SAS Jump software. So there was a PDF that was like 100 pages or more. And part of what it talked about was the design of experiments in the Taguchi. So I have used SAS, the base SAS and SAS Stat and Enterprise Miner, but not the Jump module. So they may have some design of experiments information in there as well. So I haven't used the SPSS, or I don't know, you're familiar with R. Has there been much discussion in R or R libraries about design of experiments to plan your data mining?
We do a lot of cross-validation.
Okay, but it's not necessarily like planning out what parameters you're using in the support vector machine, libsvm, or what parameters you're using in the R part for the tree.
We use cross-validation to determine what those parameters should be.
But then the parameters you're using, are you searching like all combinations of parameters? Like for the support vector machine, if it's 10 choices by 10 choices, then it's a grid of 100. That's probably doable. But if it gets to be more than 2 or 3 dimensions, then it gets to be less doable. So I guess SVMs would run quickly, depending on what fits in memory. So, yes? Sure. So with first of all, let's say I have 1,000 records I've pulled out of my training set randomly. Okay. And so for each 1,000 records, and let's say I have 100 input fields, just to pick a round number. So that's going to be the input to the sensitivity analysis. Each record, so let's say I'll start off with Mr. Smith. So for Mr. Smith, I'll input the 100 fields, and I'll get an output forecast of, say, 0.5. And then I'll input the same input record, but with the first field multiplied by 1.05, so it's 5% larger. And I look at what that output is, what's the delta between the original target. So if this original forecast was 0.5, this one is going to be 5 or 0.55, the delta will be 0.05. Okay, so now I'm going to have an output table that's going to have, for Mr. Smith, what's the change based on a fixed increase in field 1. So that'll be 0.05. Then you might get negative 0.2, negative 0.9, 0.8. And so you get all these deltas. And so if you have 100 input fields, you'll have 100 deltas. Then yeah, so first you do the sensitivity analysis, and then after you do the sensitivity analysis, then what you can look at is what records, you rank all the fields by, what's the most sensitive, most predictive, next most sensitive, next most, going down. Now, if you have your fields binned, then it's easier to convert them to reason codes. If you just have something like days late, max days late payment, and it has values of like 0 to 150, then if this is the most sensitive field, you can't really create the reason codes. So if you want to create the reason codes and you know that going into your project, one of the things you can do is try binning your fields, so then you can, any field that comes out can be converted to a reason code. Or what you could do is, if you're doing the 5% increase, if you do a 5% increase on the number of days, like if it's 0 to 150 days, you could bin it at the time you do the sensitivity analysis and say, if it's in a low range, what's the sensitivity? If it's in a medium range, what's the sensitivity? And if it's in a high range, what's the sensitivity? Without having to change the input fields. That'd be a little bit more work, but you can still get the information out.
So that's really a two-step procedure. The first step, you do the sensitivity analysis on your model.
Yeah.
The second step, you use that model, use the optimal model to do a sensitivity analysis on the individual record.
Well, then I have that model, and then I apply that model to forecast for, say, Mr. Smith. Okay, and so not every range for every field is going to be valid for Mr. Smith. So Mr. Smith, let's say, had a max late payment of 89 days. So this field was active. Okay, or if you had max late payment and it wasn't binned, when you did the sensitivity, you could do the binning, that the original value was in this range, low, medium, or high. And then, so you have to be able to identify, what's unique about this record that applies to the most predictive fields. Does that make sense? Yeah, yeah, exactly. So it's one model, but think of it as, instead of ranking by sensitivity, you could rank by correlation. You have some ranking of your fields. And the idea is, of the ranking of the most predictive fields, what fields apply to describing Mr. Smith? And start at the top of the list. What's most predictive? What's next most predictive? And in this case, I stopped when I had two reason codes. I can go 4 reason codes, 10 reason codes. It's just going down the list in a sort order to see what applies. Yeah?
So why wouldn't you just toggle those binary values for sensitivity?
You could do that too. If you had all binary values, the main idea is have a fixed input will cause a varying output. So in electrical engineering, you have an unknown black box. And you have so many electrical inputs and one electrical output. And so you just have some fixed input. There's nothing magic about a 5% increase. It could be a 10% increase or 0 to 1 toggle.
It's the ranking issue later.
Yeah, the main thing is fixed input changes cause variable output change. That's the takeaway. That's where you get something out of it.
In this, how do you handle categorical variables if, I guess, you cannot really increase them?
Well, I mean, if the internals is something that's fairly continuous, like a neural net or a regression, you can. Because if it's, you know, again, like you have a weight times a field value plus a weight times a field value. So if the field value is normally 0 or 1, but now you multiply it, now it has values of 1.5, I mean 1.05, I should say, then, and that causes a big change in output, that's a significant one. And maybe the 0 happens 99% of the time and the 1 happens 1% of the time, but when it happens, it's very significant. So you might get some values that are invalid values in the sensitivity analysis, but you can still get some kind of ranking or some kind of, gee, what's the response? And the main thing is that'll capture a lot of the interactions. So if you have, you know, many fields interacting to one hidden node, or you're doing some kind of ensemble method, and you know, these 3 fields combined into this decision tree, and these 5 fields combined to be significant in the support vector machine, and you average those 2 together, and the complexity is pulling your hair out. You just have to vary the fields one at a time, and you've got the interactions. So even though you're varying the fields one at a time, if your fields catch interactions, then this will catch the sensitivity analysis will catch the interactions.
So, and once I have sorted these fields, how do I use them? I guess what's the model is kind of the same. So where do you?
Well, so this is to describe a model. So you have a model that you're not training anymore, you're done. So I've got my final model that I'm ready to put into production, and I'm creating the PowerPoint to show the check writer. Or I'm going to put into production to create the record level reason codes. And maybe that'll be used to pick what banner to show the person. And so then this will be a one-time process to come up with a descriptive analysis to describe an arbitrary modeling system. So the sensitivity analysis is used as a ranking, and sometimes I'll create a bar chart that the 0 axis will be like this, and I'll have large values of one sign, large values of another sign, and it'll be like a funnel. And the magnitude sorting at the top will be the most significant going down to the least. And I'll just have the variable names by each one of those. And then you can see by the funnel, you can get both the magnitude and the sign to see what affects the sensitivity, taking into account all the interactions. Yeah. Not that I've programmed from scratch. Sometimes what I've done is train like a small decision tree, even if I did something else fairly different, just because I can show that on PowerPoint. So I might show a breadth first view. That might be the decision tree with 8 leaves that I can fit on one slide, and then maybe a few rules that go all the way down to the most desirable fraud segment, or something like that. And then I would set expectations. Hey, I'm describing the amount of detail that's in a bike, not in a car. This will give you the high level dynamics of what's going on, but it's not every last detail. So, any other questions? Yeah? Huge amounts, absolutely. Well, that's in the data versions. That's what I change between the different data versions. So, yeah, so in the data version 1, I'm not doing much pre-processing. I'm kind of, well, let's get the most obvious things that are quick to program in kind of an agile process. Let's get something working through the entire system to a functioning forecasting model. And then I look at the results, I see what's already predictive. Now I have ideas to program much more complex things, and that would be data version 2, or I capture more complex interactions. So data version 1 is kind of find out what are the univariate most predictive fields. Data versions later on will be more of the interactions, or what are more of the modeling or simulation, or what's the human behavior, or different aspects like that. So, I mean, if I'm doing fraud detection, then what are additional use cases of fraud, or mules, or money laundering, or different things like that. And so then I keep adding complexity, and I'll see my model results improving, but then as they level off, that's why I stop before I get to data version 5. I say, nope, I should go to the next project. So I'll get jumps from data version 1 will level out here, and then when I start data version 2, it jumps up a little bit. And then it keeps going a little bit more, and then data version 3 jumps up a little bit. And then it asymptotes. So between each data version, the reason I continue on is the pre-processing and the trying to understand the data systems, or what you're trying to analyze. So yeah, that's at least as much as this. Yeah? Like in a data version, I'll start off with a series of models, of data version 2. I'll try 10 more decision trees, 10 more neural nets, 5 more of this, 5 more of that. And then if I want to combine and take the best of this one, this one, this one, this one, feed them into like a regression to come up with, gee, I'll weight this forecast times 0.5 and this forecast times 0.3 and so on as a model combining for like an ensemble method. And then that would be like the end of data version 2. And then, okay, I've pounded this and I'm not squeezing any more water out of the rock, go on to the next data version. Or I'll just have it time boxed. I'll just say, okay, I'm working on each data version for only X period of workdays. And then I stop wherever I am and I go on to the next one, because I have to tell management how long I'm working on a project. And they need to plan when I'm going to start the next. So a lot of times time boxing works well just to keep me moving and set expectations. So other questions? I had challenges bringing R into my company because it is open source. And they had questions on, gee, can you verify out of the 1,800 libraries or 4,000 libraries that none of them has a virus in it? And if we're bringing it into where all our financial data is, we don't want any of that leaking out. And so there was all of those legal questions and compliance questions and security questions that for many people, what would be attractive about R was scary. So I would say it's not so much the quantity of algorithms as the flexibility. And I have a general attitude of there's no silver bullet. So I would rather have some choices like, get something that's broad, like Enterprise Miner or R, and then maybe a category killer like Selfridge Systems that has a very good tree, or Bayesian that has lots of Bayesian networks. That's very good and very deep, but maybe it's narrow. So I'd rather have a complement and then just kind of be internally competitive. I'd rather have myself compete against a team member than myself compete and lose against another company. So I'd rather foster internal competition than lose external competition. Well, thank you for your time.